We have a second problem to give you practice using the logistic growth equation. Our second problem says that aphids are infesting our yard. Population exhibits an R of 2.25 aphids per day. A single bush in our yard can support 1 million aphids. And then I ask you to calculate population growth rates for two different population sizes, and then I ask you one more question. So it's a word problem that's to us in the problem. So this problem exhibits an R of 2.25. Our carrying capacity for our single bush is 1 million. All right, so question A says if we have a population size of 10, so 10 aphids colonize our bush, then what is our population growth rate? Our population growth rate is dN over dt. How do I know this? Well, in the problem, I'm given R, and the problem tells me the carrying capacity. Since I have a carrying capacity, I know that I'm using this logistic growth equation. So here's our equation. We can also use this one, and this is the one that I prefer to use. It's a little bit easier to use our calculator to solve our problem. So with A, we're going to start with population size of 10. We are calculating our dN over dt, and I'm just going to substitute each of our variables into our equation. So we have our R, 2.25, times our colonizing population size of 10, times 1 minus 10 over 1 million. And when I do this, when I solve it on my calculator, I get 22.4998 aphids per day. Rounding to a whole number gives 24 aphids per day as our growth rate. So that's question A. Question B changes our population size. Now, let's assume the aphids have had time to grow and reproduce on our plant. So now we have 750,000 aphids. So just as before, I'm going to use this logistic growth equation and substitute each of our variables. So 2.25 times 750,000 times 1 minus 750,000 over 1 million. And when I solve this equation, I get 421,875 aphids per day. 421,875 aphids per day. And this equation actually gives me the whole number. I do not need to round. So that's B. Question C is a little bit different. So I don't ask you for the population growth rate. Instead, in C, I ask you what population size exhibit the largest population growth rate. Now I can look at these and I could say, yeah, this is a pretty large growth rate, and that's larger than that, but that's not what the question's asking. It's saying what population size on our plant would exhibit this maximum value of this dN over dt. So what we're asking for is this max dN over dt value. And what is that? Well, that happens when our population size is half of our carrying capacity. How do I know that? It's just given to us. It's a fact, and it's based on our logistic growth equations. So here's our sigmoidal curve. We grow up to our carrying capacity, and this graph represents our population size as a function of time. We want the point where the slope of our line is the maximum value, and it happens right at that point. And that point represents half of our carrying capacity. So just based on our equations, our maximum value is going to occur at half of our carrying capacity. Half of our carrying capacity is 1 million. Therefore, our population size will be 1 million divided by 2, or 500,000. Population size of 500,000 would exhibit the maximum population growth rate.